Now we see the numericals in quantum mechanics and lasers. Now calculate the de Broglie wavelength associated with an electron having a kinetic energy of 100 eV. Now we have already seen that kinetic energy of an electron, if it is given, we have to calculate the wavelength of the electron. So we use lambda is equal to h by root of 2me. Now what is given here? Kinetic energy is 100 electron volts. It is given. Electron volts can be converted into joules by 100 into 1.6 into 10 to the power of minus 19 joules, or me is equal to 9.12 into 10 to the power of minus 31 kg. We know that mass of electron and we have to calculate the wavelength of the electron. De Broglie wavelength of an electron. Lambda is equal to h by root of 2me. This is the formula which we have derived in the sessions, where E is the kinetic energy which has been given as 100 eV. So substituting the value of h to mass of electron and the energy in terms of joules, we have converted, substitute and do the calculations. You will be getting the value as 1.227 into 10 to the power of minus 10 meters. Next, one more. Find the de Broglie wavelength of an electron accelerated under a potential difference of 100 volts. When the electron is accelerated through a potential of 100 volts, we know the de Broglie wavelength lambda is given by 12.28 by root V angstrom. This is a formula which we have to use to calculate the de Broglie wavelength when it is accelerated through a potential difference of V. Here acceleration potential is 100 volts and mass of electron we already know, and here directly we can use lambda is equal to 12.28 by root V into root V angstrom. So substitute value of V into here, it is a direct root of 100 is 10. So it is a direct application 1.228 angstrom. Next we look at another thing. Calculate the energy in the first excited state of an electron in an infinite potential well of width 2 angstrom. So here it is been asked as first excited state. Calculate the energy in the first excited state. What is the energy in the first excited state? Means n is equal to 2, as n is equal to 1 is the ground state or 0 point energy. So for first excited state, n is equal to 2. What is the width of the potential? A is equal to 2 angstrom. Angstrom is 2 into 10 to the power of minus 10 meters. So mass of electron is 9.1 into 10 to the power of minus 31 and E is 1.6 into 10 to the power of minus 19, and H value is already given a constant value. So what is the energy eigenvalue for the potential, infinite potential well is En is equal to n square h square by 8m a square. Here what we are getting here, n is we are taking as 2 because it is asked to find the first excited state. So n is equal to 2 is the first excited state. So substitute value of n as 2 here and substitute all the values here. You will be getting the substituting m is mass of electron, a is nothing but the width of the potential wells here, 2 into 10 to the power of. So substituting all these values, you will be getting the energy in joules. Energy is to be expressed in electron volts divided by 1.6 into 10 to the power of minus 19. So you will be getting 37.74 electron volts. This is another problem. This is the most important problem because here it is been asked as first excited state. Remember, n is equal to 1 is for the ground state, and for the first excited state n is equal to 2. So we have already derived the energy eigenvalue En is equal to n square h square by 8m a square. It is n is a quantum number. So here we are doing this problem in this way. Next, calculate the energy in the ground state and first excited state of an electron in an infinite potential well of width 1 angstrom. Similar to the previous problem, the only thing is here it has been asked as energy in the ground state and the first excited state. First excited state means n is equal to 2, ground state means n is equal to 1 for an electron in an infinite potential well of width 1 angstrom. So Me is equal to 9.1 into 10 to the power of minus 31 kg. We know that mass of electron, charge of electron and value of H is always constant. Here it is ground state, so we are taking n is equal to 1 and n is equal to 2 is the first excited state. So we are going to calculate E1 and E2. So here we know that energy eigenvalue of a infinite potential well En is equal to n square h square by 8m a square. So E1 is equal to, put n is equal to 1, substitute the values, and here A is taken as 1 angstrom, A is nothing but 1 angstrom is 1 into 10 to the power of minus 10. So you are getting 6.0838 into 10 to the power of minus 18 joules. You can convert this into electron volts or keep it, it is fine, no issues. Now we go with n is equal to 2 for the first excited state. Since we got E1, we can take it as E2. Here En is equal to n square into E1. As n is equal to 2, directly put the value of n as 2 and 2 square is E1. Since you know E1, you can find out the value of N2 directly from this formula, because En and E1 are related in this way. En is equal to n square into E. Substitute n is equal to 2, you will be getting first excited state E2 as 2.412 into 10 to the power of minus 17 joules. Can multiply E1 into 4 because 2 square is nothing but 4. Okay, next, this is a problem in the lasers. A pulsed laser with the power 1 milliwatts lasts for 10 nanoseconds. If the number of photons emitted per pulse is 5 into 10 to the power of 7, calculate the wavelength of the laser. So what is being given here? Power is given as 1 milliwatts. Milli means 10 to the power of minus 3. So converting into minus 3. And lasts for 10 nanoseconds. That means lasts for 10 nanoseconds. That means time is equal to 10 nanoseconds. Nano means 10 to the power of minus 9. Next is power per pulse. Number of photons. N is equal to 5 into 10 to the power of 7. H value is given and value of C is 3 into 10 to the power of 8 meters per second. Now we know that E is equal to power into time. E is equal to power into time, and also we know that E is equal to NHC by lambda. E is equal to H nu. Nu can be written as C lambda. E is equal to NH nu. So we can write it as NHC by lambda. So both are expressions for E. We write it as P into T is equal to NHC by lambda. Since both are expressions of E, since LHS are the same, RHS also can be equated. So P into T is equal to NHC by lambda. Thereby lambda is equal to NHC by P into T is equal to lambda. N value is known, H value is given, C value is there, P value is already given. So substitute the value of P, and time is nothing but 10 nanoseconds. It is 10 into 10 to the power of minus 9. Substitute the values, you will be getting the value of lambda as 9.9375 into 10 to the power of minus 7 meters. Next we see another problem. A laser is emitting a beam with an average power of 4.5 milliwatts. Find the number of photons emitted per second by a laser if the wavelength of the light emitted radiation is 6328. What is being given here? Average power. Power is being given in milliwatts. Convert it into watts, 10 to the power of minus 3. And the wavelength is given as 6328 angstrom, which is nothing but 6328 into 10 to the power of minus 10. What is being asked here? Find the number of photons emitted per second. So we take time is equal to 1. Value of H is known and C is known. As said earlier, E is equal to P into T. But here we also know that E is equal to NHC by lambda. So P into T is equal to NHC by lambda. Here we are asked to calculate the number of photons. So N has to be calculated. Bring this lambda to here. So N is equal to Pt lambda by Hc. All the values. P is given. Time is 1 nanosecond. Lambda is 6328 into 10 to the power of minus 10. And H is the constant. C is constant. Substitute the value and get the answer. So this is the value of N we are seeing. Previously we have seen the value of wavelength. Thank you.